Hi everyone, I'm Jim White, and we're going to continue talking about thermoelectric devices. We're going to get into these thermoelectric generators, or Peltier modules as they're called, sometimes depending on how they're used. Now, there's basically two types that use different internal materials, and based on the temperature that these materials can survive, we have two types. One that has a maximum temperature of 80 degrees C, and another type that can make it up to 150 degrees C. Now, the lower temperature one it may be called a Peltier module. Uh, any of them can be called the Peltier module because they can heat or cool, but generally the ones that are used for refrigeration, uh, that type of application, or making a cold side on a cloud chamber, uh, are the lower temperature devices. When you're going to put a module on a hot stove to generate electrical power, you probably want to use the higher temperature one. Then there's the subject of potting. Uh, you see the black material around the edge here. That's a potted device. If you can see the little individual pieces in there, they'll be silver and stacked up in a nice pattern. Then you have an unpotted module. And the potting is to keep condensation from getting in there and corroding the junctions, or even causing poor thermal performance if the water is in there while you're operating. So I've seen white potting on the lower temperature modules and typically black potting on the higher temperature modules. So that might help you determine what module you have. Now, the low temperature ones seem to be available on the internet at incredibly low prices, like around $2. I assume these are factory rejects, and since there's no specifications given, uh, they probably don't meet the typical specification. They might still be useful for experimenting in some applications. So let's get into what these can really do.
Okay, here's a thermoelectric module that I have hooked up to a voltmeter on the 300 millivolt scale. And I'm just going to bring my hand near the module. I'm about 3 inches above it, and you can see the millivolts output going up. And if I take my hand away, it goes down. So there it was detecting the infrared radiation from my hand. If we painted the surface of the module black, it would probably work even better. Now the module's resting on a piece of styrofoam, and now I'm going to just put my hand right on the module, and you see the millivolts going up, and now they're coming back down. And that's because the heat initially just heated one side of the module, but now it's conducting through and heating the other side, so the temperature differential is disappearing. Okay, it's heading towards zero. And here we see the polarity has actually reversed. Now that's because the top of the module, where I was touching it, is cooling down towards room temperature, but the other side of the module is still warm from when I was touching it. The styrofoam is keeping it from conducting heat away on that side. So the heat has to come through the module and equilibrate with the top side of the module. So eventually both sides will reach the same temperature and we'll have 0 output volts. In order to learn more about these modules, you have to heat sink them. And what I'm going to use here is some aluminum channel, and you need some heat transfer compound. And basically what you do is coat the area where you're going to mount the device with a very thin coating of the heat transfer compound. And then do the same thing with the heat sink that'll get mounted to the other side. So we're going to mount the device there, put heat sink compound on this channel, and then these are power resistors. They're packaged like a power transistor or a power FET might be, but I'm going to mount those to the top heatsink so that we can heat up one side while cooling the other to see what's going on. Now, if you go to tetech.com, you'll see details on how to mount the devices. And if you go to mcmaster.com, you can find the aluminum extrusions that you can make your own heat sinks out of. And here's an example of other shapes of extrusions that you can get. You can get deeper ones, wider ones, and you can put them together to make your own heat sinks. Now, TE Tech tells you to use stainless steel screws, and the reason is stainless steel is a very poor thermal conductor, so that'll transfer less heat from one heat sink to the other. Plus they tell you to use a fiber washer to help get maximum efficiency. They also tell you to use compression washers, which are also known as Belleville washers, and they're shaped in little domes so that they can actually compress a little bit and maintain force, but still allow some thermal expansion without it causing undue pressure on the device that's sandwiched between the heat sinks. So I'm going to go ahead and do all that, and then we'll resume. Okay, here's our setup as I described it, and the Thermoelectric device is installed in there, and I have a thermocouple installed right under the device and one right above the device. The heating resistors are connected in parallel and going off to my power supply. After a couple test runs, I found that I was close to exceeding the temperature rating of those resistors, this type of resistor. So I'm going to change the arrangement and utilize more resistors in parallel, before we get into the actual tests. Okay, here's our redone module. The thermoelectric module is in there. We have a thermocouple on the bottom, and there's a thermocouple in the middle here. And that's 6 24 ohm resistors in parallel. So that's 4 ohms, and it's connected to our power supply here so that we can deliver heat to the top of the module. I plan to keep the bottom part cool by placing it in a tray of water, perhaps even ice water. We'll see how the testing goes. Okay, here's our setup ready to go. What we're actually trying to do is create a temperature differential between the two faces of the thermoelectric module and see how much voltage and in the end how much power the device can deliver to a load. These blue resistors are each 1 ohm, and there's 6 of them in series, and with the gray alligator clip we can put a load across the device and see how much the voltage changes. Then we can calculate the power into the resistors. So at the moment I have very cold water in the tray here, and we're reading a 2.7 degree or 2.6 degrees C between the top and the bottom plates of the thermoelectric module. And at the moment we have 0.1 volts. So I'm going to put some power into the resistors. I'll start with 15 volts. And you can calculate the power. That's basically a 4 ohm resistor with 15 volts across it. And we can see our temperature differential is increasing and the voltage output is increasing. The top temperature there is T1 minus T2, so that's the difference on each side of the thermoelectric module. The bottom temperature is T1, which is the temperature of the top plate. Now, if this were a low temperature module, we would not want to exceed 80 degrees C on that top plate. So T1 is starting to get pretty close to our temperature limit. So I'm going to reduce the power. So I turned it down to about 12 volts. Slow the rate of rise there. Okay, we're nearing 50 degrees. I'm going to put the 6 ohm load on, and our voltage went down to 1.9 volts. Now I'm going to drop that down to 4 ohms, and our voltage went down, and we're still hovering near 50 degrees, but it's going down. As we suck energy out of the device, its temperature is going down. Now I'm going to remove the load, and you see the temperature difference starts going up again. Now I'm going to go to the 2 ohm load, and you can see the voltage there. And again, the temperature is falling. Now I'm going to go down to the 1 ohm load, and we're down to 0.75 volts, and you can see the temperature difference is going down as we suck energy out of that thermoelectric device. So now we can do some calculations and see how much power we were actually delivering to the load. I'll calculate that and then we'll resume. Okay, here's the results of our testing. While we were warming up the device, when we had 15 volts applied, we were delivering 56 watts to the plate on top of the module. Now that's while we had very cold water cooling the bottom heatsink. Now, we later reduced the power to slow down the rate of rise of the temperature, and it turns out it actually set the supply to 13 volts when I said 12 volts. And here's the table of our results. We have the temperature differential, the load resistor, the voltage, and then here I've calculated the currents, and here I've calculated the watts delivered to the load resistors. So without any resistor connected with the 50 degrees C differential, we had 2.73 volts. Then with the 6 ohm load, at that temperature, we had 1.9 volts, so that's about 0.3 amps and a power of 0.61 watts. And here's the results for the other resistors, load resistors. It's kind of interesting how constant the power remains over such a wide range of load. Our maximum output occurred with the 2 ohm resistor, and if we calculate the efficiency based on that, we had an efficiency of 1.7%. Actually, I'm sure it was worse than that because we would have had to crank our power up to overcome the cooling that the load current was causing. So with the 2 ohm load, we can get 1.2 volts. So if we had 10 of these in series, we could get 12 volts at 7.2 watts. It's not too bad, but you can see it's not that easy to do. Okay, let's try one more thing before we let it go. I've removed the power connections to those resistors, and I've hooked up the power supply to the thermoelectric module wires. And then I also have a voltmeter reading the voltage to the thermoelectric device. And see if I can, there's a puddle of water that I've put on that plate, and all the little droplets you see are from when I was running it earlier. We had condensation form on the plate by going below the dew point of the air. Now I'm going to turn on the power supply and go up to 4 amps. And at that point we have 9 1/4 volts. And T1 is the temperature of the top plate, and T2 is the temperature of the plate that is in the water. And as you can see, the top plate is getting colder. So we're pumping heat out of that plate and dumping it into the water. So we're acting as a heat pump now. So as we go below 0 degrees C, we should be able to freeze the water that's on the top plate. Now, the thermocouple's in the center, and it might take a little while for the edge of the plate to get that cold. There, I hope we can see the water. So we'll just wait a little while, and it should freeze. There, I think you saw that. It froze rather quickly. So if we let this run a little while, all those other droplets may have frozen. It's kind of hard to tell. But frost should form on everything if we let this run and get below the freezing temperature. Moisture should come out of the air and condense and then freeze. So we'll just wait a while and see what happens. Okay, if you look at the screw heads on the 3 right-hand resistors, I think you can see the frost has formed, and that's just moisture from the air condensing. And let's look at something else. What I'm going to do is disconnect from the power supply, but still leave the voltmeter attached. Okay, and you see we're producing 1.8 volts out of the unit just due to the temperature differential. And this time we have a very cold top and a cold heat sink on the bottom that's sitting in cold water. But as long as there's a temperature differential, we're generating voltage. So you can do the same thing with temperature differential at cold temperatures as you can do at hot temperatures. So that's about it. See you in the next video.